Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Now you join us today for a webinar called Sublime Precursors, How Modelling Organometallics at Surface Drives Innovation in Materials Processing. We'll be looking at atomic scale simulations of organometallic complexes as precursor molecules for the deposition or etching of materials. And as you can see on screen, we'll be joined by Simon Elliott. Now, he's a director of atomic level process simulation at Schrödinger. He'll be focusing on three key precursor properties, that's volatility, reactivity, and decomposition. And these properties are vital in materials processing, or understanding them is really key. He's also going to present some simulation workflows that integrate quantum mechanics with automatic structure generation, showing the thermodynamics of adsorption during growth or etching and the reactions that are typical of thermal decomposition. So we're hoping that there's a few key things you will have taken away by the end of today's webinar. You'll have learned about the key properties of precursors that are critical for nanoscale materials processing. You'll have gained a firm understanding of how atomic scale simulations are utilized to predict the volatility, reactivity, and decomposition of organometallics at surfaces. And you will have seen some practical examples of how machine learning technologies are implemented to drive innovation in materials processing. Now, we send a copy of the recording to absolutely everybody who registered. And one thing that we're keen to point out is that we don't share the slides from our presentations. The reason for that is that we think it's more important to hear what's being said and what's being demonstrated on screen, not just the content of the slides themselves. Now, that's quite enough from me. I should now hand over to our guest, Simon Elliott. So hopefully we will see him on screen soon and then see his presentation. And we should be able to hear him as well. Simon, we can see you now. Thank you so much for joining us. We're really appreciative of the time that you've given over to this. Very interesting topic. I look forward to seeing the presentation. So take it away.
Thank you very much, Ben, and thank you to Chemistry World for this great opportunity. I'm delighted that so many have come. Thank you for coming to this webinar. And as Ben nicely outlined, today we're going to be looking at deposition and etching from precursors, from chemical precursors that are used for these processes, organometallic molecules, organic molecules, and these are interacting with surfaces and causing the growth of materials. So it's a really interesting area that brings together a couple of different areas of science. And our approach is to look at it with computational modeling. Schrödinger is a modeling provider. So that's the focus of today's talk. So I'll head on. Schrödinger offers simulation tools that really are focused on answering questions that are important for technology. And we cover a wide range of technologies and industries. Some of them are shown here with a few graphics, everything from organic electronics for displays, through catalysis and energy capture and batteries, consumer goods. Today we're going to talk about thin films, deposition, etching, the processing of films, and how chemistry drives these kind of materials growth events. This is really important for the semiconductor industry, for growing functional films, for solar cells, batteries, and also protective films and coatings. So it's an area that underpins a lot of other technologies, and maybe it's something of an invisible application of chemistry. People don't realize how much this chemistry goes into all kinds of devices and products that we have in our everyday life. So generally, I suppose the theme today is how modeling can help in this area of research. And I'd like to draw the analogy to the automotive industry. So the automotive industry is undergoing a digital transformation. There was a time when you sat into a car, it may well have been designed with the help of computer-aided design, but you weren't really aware of that. The user just drove the car. We've now come to a point where there's a lot of interaction between the driver and different automatic computer-driven systems in the car. So really, those systems have become so easy to use that you can, as it were, trust the driver to be interacting with them. So there's automatic windscreen wipers, there's lane assist, there's automatic braking. You know, even the mechanic has to turn on a laptop to diagnose what's wrong with your engine. So you can see all these the digital driven processes are becoming democratized and really accessible to everybody. We're moving though towards a point where with all the sensors and the data being collected right across the automobile, that can all be integrated, and we can get to a point where actions can be taken on the basis of all that data without the user intervening in many situations. And we're moving towards this autonomous driving vision or future. There's a lot of debate, of course, about how exactly that's going to happen and whether it should happen, but it is a transformation that's taking place, that even in this area, things are becoming a lot more digital. So this is common across lots of different areas of life. If you think of maybe banking or media, there was a time when journalists looked after media. Now we're all publishers and content producers. Retail has moved online. So digital transformation is really something that's affecting lots of areas of our daily life. How about research? Are we at that point at this stage? Now, models are always, of course, central to the research process. You make a model of the data to explain it. Computational modeling is just one way of embodying those models. I think we're also going on a journey with computational modeling. There's a time when computational modeling is seen as a specialist discipline, that really only specifically trained people with special equipment can do it. Building on from that, there's a sort of democratization level where the software becomes so robust and well understood and well validated that a lot of different researchers can use it, even if it's not their primary area of speciality. And it becomes more of a design tool that is part of a wider integrated research activity. And finally, maybe we're moving towards a point where data becomes so well integrated that there's really no distinguishing between experimental data and computed data, and it's more about access to the data, action, based on data, and analysis of very large data sets, which feeds into the sort of very topical area of machine learning and automation, artificial intelligence. So this is sort of the overarching umbrella of what I'd like to speak about today. And I'd like to move to a poll where we see where we think we've got to with the R&D process.
Indeed, yeah. So the poll should be on your screen now. So it's a very simple question. Where is your organization or research group on the digitization journey? Are you at the stage where modeling is a specialist discipline? Is modeling something that is accessible to all researchers? Or are you at the stage where all data is integrated and actionable? And it's really useful for us, for you to complete these polls. It helps us know, again, as I was saying earlier, what sorts of events we should put together for you as an audience, but it also helps speakers like Simon to know how much detail they can go into, where they can lead their presentations in future and so on. So please do just take a quick minute to click and vote in this, and we can see a running total of how many people have voted. So I'm going to leave it for a few more seconds to allow a few more people just to have their say and help us to really understand who our audience are today. So well, at least half of you have voted. I think we can get a few more votes in the last few seconds. So just a little reminder, especially for those who came in late, we'll send you a link to the recorded version of this webinar in probably a day or so's time. Keep an eye out for that. And for those of you who attend live, there will also be a certificate in there. That is a really good way to catch up with anything that you missed or anything that you just weren't quite certain about at the time. And obviously you can come back and watch that in a week, a month, a few months time if you want a little refresher further down the line as well. I think it's probably enough of you voted now, so we'll close that poll and we'll just get those answers on screen so we can see roughly where people sit in the audience. So 53%, just over half, saying modeling is still a specialist discipline. A third of the audience, it's saying it's accessible to all, and just 14%, so definitely in the minority, with all data integrated and actionable already. So Simon, we'll come back to you. I mean, do you think that broadly represents the industries that you work with, or do we have an outlier for an audience?
No, I'd say that's fairly typical. Yeah. That's still lots of people see the sort of modeling as quite a specialist thing, but we're gradually pushing forward with getting more people using it in a more democratic way, and it's probably true that a full integration is still some way off in the future. I think that's a fairly representative result.
Excellent. Well, thank you. And I guess all of these things, they always have some momentum as we see these sorts of changes happen to the way that people work. So it's good that we are on the front of that wave. So thank you, Simon. I thank you, everybody, for completing the poll. And I'll be back for a bit more later on. Simon, I'll hand back to you.
Ben. Okay, so today's agenda then is to look at where we are on that transition between a specialist discipline of modeling that operates in isolation, a more, say, democratic, a more user-friendly set of tools that people can use and really contribute to their research, and then the final use of big data. So I'll just, right. So the first part is to consider what kind of design questions we might have in this area of deposition, etching, and the processing of thin films. And anytime we look at designing new chemicals, we always come across this rather surprising fact that chemical space is really, really big. So let's look at how big it is for the type of systems we're looking at. For organometallic precursors, of course, you need to have ligands surrounding a metal center, and the chemical space of ligands is really very large. Here's the most common ligands that I've seen in this area. There's maybe 100 here. You can group them into families, say the 9 families here: diketonates, carboxylates, amidonates. And each one can be modified by the alkyl groups that are on it, or the nature of the bonding between the ligand and the metal. So let's just look at one example, an amide, so a dialkylamide, a very simple ligand consisting of nitrogen with 2 alkyl groups attached to it. And if we enumerate over the alkyl groups, we could let them, for example, be methyl, ethyl, N-propyl, isopropyl. Let's just consider 8 alkyl substituents. You could probably dream up a further 8, 10, or 12 easily yourself, but just looking at, say, 8 alkyl substituents on the alkylamide, you already get 36 different possible ligands. And that's just one small family. If we now look at all the different families that I mentioned there, and enumerate over the R groups, over the alkyl groups, we straight away get up to well over 1,000 different possible ligands. So it's quite a large space. If in addition you substitute sulfur for oxygen, you can get another 794 ligands. Substitute phosphorus for nitrogen, you get another 1,000 again. Easily 3,000 ligands. Maybe substitute trifluoro for methyl, you can double the number again. So very easy to get up to large numbers of ligands that we have to consider in the chemical space when we're designing a new precursor. And of course, it's interesting to think about how many of these precursors have already been explored. So if we have 1,000, say, ligands, and that means there are 1,000 homoleptic complexes, so complexes with just one ligand surrounding the metal center, repeated identically. A typical set of experimental studies only has looked at a fraction of this. So this is a common database for atomic layer deposition. It's called atomiclimits.com. It has a really good overview of the literature. And I checked there to see how many iron precursors there were, just as an example. So there are 15 different iron precursors, and they're sort of shaded in here on the map. That's maybe what is typically looked at experimentally. What can we compute? Well, if we're doing, say, density functional calculations, so quantum mechanical calculations, we can easily compute 10 precursors in a day, say 12 hours on 8 CPUs. If we wait a little longer, we can run 100 precursors in 3 days on, again, modest computational resources. And if we have more resources or we wait longer, we can do DFT optimizations of maybe more precursors, but that's kind of the order of magnitude that you can easily do. You can easily scan through 100 precursors at quantum mechanical level. If we could probably get up to the full 1,000, but if we then move on to heteroelectric precursors, precursors that combine 2 or more ligands, the number of possibilities just starts to explode. So we easily get up to 1 million different possible ligands by combining different possible precursors by combining the different ligands with one another. Now, this really does provide a challenge for computational modeling and screening. I highlight here a recent paper, not in the area of precursors, but in the area of organic materials for displays, where my colleagues did 250,000 DFT calculations. So this was really a huge computational effort. That's probably what we can think of as the forefront of state of the art nowadays in DFT. So doing 1 million structures really with DFT is not possible. So we have to think of ways that we can screen 1 million structures quickly, then do more precise quantum level calculations on maybe 1,000, 10,000, or even as here, 250,000, and then narrow down the number of possibilities to something that can be looked at experimentally. So that's what we're going to try to do today in an overview. I won't go through that entire process. Obviously, it's a bit of a vision. So we'll go through the 3 different essential properties, as Ben mentioned. The essence of deposition and etching consists of evaporating the precursor. When the precursor in the gas phase reaches the reactor, the deposition reactions should happen and cause the thin film to grow. And then as the precursor has a lifetime in the reactor, it can start to decompose. And this is generally thermally driven. So above a certain temperature, decomposition can take place, and that can cause impurities. So these are the 3 key properties that we want to address and we want to design against. There are other properties too, but really if these 3 can be considered, then you have a very good chance of having a successful precursor. So the first thing is volatility. And this is a case where we see, the possibilities of big data and the way to screen over a large number of different possible precursors. The example that I'd like to show you is for molecular layer deposition. In this case, the precursors are actually organic molecules or a mix of organic and inorganic. And again, it's all about finding a process window where the deposition reactions take place at a temperature and pressure and other conditions, and aren't limited too much by the need to evaporate. So the evaporation temperature is a lower bound, and the decomposition temperature, which is the upper bound. So if we can adjust those evaporation and decomposition temperatures, we can get a nice wide process window for a successful molecular layer deposition process. And that's where the design process will come in tuning those different temperatures according to the chemistry that we want to design for. So I want to present our new capability in computing volatility and finding these evaporation temperatures. The lower the evaporation temperature, the more chance we have of finding a successful process in MLD. This is the machine learning model that we've developed for evaporation temperature. We put together a training set of literature data for the pressure temperature relationships for the evaporation temperature or sublimation temperature of over 1,000 organometallic complexes that are typical for the area of vapor phase deposition. This spanned 78 metals and 300 ligands, and in fact there were 3,000 data points in all because we had multiple data points for many of the complexes. Machine learning is a way of doing a very complex fit across many variables. So the first thing is to work out the variables, and these are called descriptors. So we take the chemical structure and we abstract it into descriptors that describe things like the polarizability or the mass or the elements that are there or the number of rings or chains. And in fact, these descriptors were all just based on 2D sketches of the complexes. So we didn't have to do any quantum mechanical optimization or any further high-level calculations. So just a sketch of the structure of the complex, and then we're able to develop the descriptors. Then the descriptors were fitted against experimental data. And you can see the results in the graph. So this is a correlation graph of the experimental data on the x-axis, the reciprocal of the temperature, the evaporation temperature, and the predicted evaporation temperature on the y-axis, again, the reciprocal. We trained against 80% of the data, and that's shown in orange. And then we reserved 20% of the data as a test set, which the model hadn't seen before, and checked to see how well the correlation was for that unknown set. And you can see that the results are really very good. The points both for the training set and the test set lie on the 45-degree straight line pretty well. The R squared is a measure of the quality of fit, and that's 0.99, so practically the optimum value of 1.0. The RMS error across the entire data set is 16 degrees Celsius. The mean error is 9 degrees Celsius, or 9 Kelvin, which is 3% of the evaporation temperature on average, if we restrict ourselves to the 54 most frequent metals that we had in our training set. And what's worth bearing in mind is that once this model has been created, it's very quick to evaluate. It takes a fraction of a second. We can probably obtain 100 temperatures per second from this machine learned model. So very suitable for screening large data sets. Here's the coverage by element. It's very uneven. So the shading here shows the number of data points we had for the different elements in our training set. So this is the set that we used to generate the model. And the non-metals, we had a lot more data, a lot easier to find. And so the error is correspondingly lower. Some of the transition metals, the error is a bit higher because we had less data, but you can see very good extrapolation. So even where there are 5, 10, 15 data points, the fact that it's part of a larger model gives a really, really low error, as low as 10, 15, at worst 20 degrees Celsius. So more than enough to make a prediction about whether something is volatile or not. Here's an example, gold. These are the gold complexes that we had in the training set. There were 106 data points here, and the error was similar to what I've said before, 11 degrees Celsius or so. And these again are the correlation graphs of the predicted temperature on the y-axis against the experimental temperature on the x-axis. And I just blow up there the area between 0 and 200 Celsius because that's probably the more interesting area for our applications. Here's one specific example from that gold set. It's a complex trimethylsilyl gold with a trimethylsilylmethylene phosphorane. And this comes from the group of Sean Barry and Carleton University. And these experimental data are Clausius-Clapeyron plots, so the log of the pressure against 1 over temperature, derived from thermogravimetric experiments. And I've shown the 3D structure just to give you an idea of what the structure is, but in fact, you don't need it for this model. You just need the 2D sketch, as I said before. And from this sketch, we can predict the vapor pressure as a function of temperature. And here it is, the blue line shows our prediction. So in this case, actually, the error is way down around 3 or 4 degrees Celsius. Very good agreement for this particular compound. Now, as I said, we're going to look at molecular layer deposition today, not the normal chemical vapor deposition or atomic layer deposition. So for that, we're actually going to look at organic precursors. So we have a model for organic precursor volatility as well. We generated it in a very similar way. We actually had an even larger data set here. People have been collecting data on the volatility of organic molecules for a long, long time. And there's some really nice data sets out there. So we had a data set with 12,000 points. And this we were also able to fit against in a very similar way. So I won't go into it in huge detail. You see there the correlation of, again, the predicted temperature against the experimental temperature. And the error here for the neural network that we used is around 2 degrees Celsius. There's some references there to comparable literature which exists. Other people have made models for organic volatility before. Their errors are slightly larger. So here's the typical performance of the organic volatility model. You can see the dashed lines are the predicted values and the dots are the experimental values. And these are 4 compounds that weren't included in the training set. So nice transferability and good predictions. So the example that I'd like to talk about is molecular layer deposition. This is a way of depositing organic films or hybrid organic inorganic films. And here I've just stolen some nice cartoons from the review article by Marit Karppinen, which is one of the top groups in producing these type of films. And you can see the schematic there of how the films are produced. The organic groups are linked by reactive moieties, and each one is laid down sequentially one after the next. So you get a green layer, then a purple layer, a green layer, a purple layer, as you turn on and off the precursor pulses. Alternatively, you can include an inorganic metal, and that's shown in the next cartoon to the right there with a blue metal ion. So the precursors should be organic molecules, but with reactive moieties that can be used to both bind to the previous reactive surface and generate a new reactive surface for the next pulse. And a very frequently used molecule is hydroquinone, or benzene 1,4-diol. You can see it's bifunctional. It has two OH groups, so one can react with the existing surface, and the other OH group is still available for reacting with the next layer when you let in the next precursor molecule. So it's a rigid molecule that behaves like that. So this is often used. Unfortunately, it's not very volatile, so we thought we'd look and see can we improve on it. So this is our sort of strategy. We start with the base molecule, hydroquinone, and we look at modifications of it. We can change the R groups, change hydrogen to methyl or ethyl or isopropyl, for example. And this gives 176 different possible molecules. So again, even just a small enumeration over just a couple of R groups, already we get into large numbers of molecules. We don't need to do any special work on these molecules. We just need to sketch them and put them into a topological description. This is called a Smiles string. If you know what that is, that's fine, but it's just a way of describing the bonding between each atom in the molecule. We then feed it into the model, evaluate the descriptors for each molecule, and using those descriptors and the existing model, we get a prediction of the volatility of the evaporation temperature. So here are the results for benzene 1,4-diol. I've plotted the predicted temperature on the y-axis against molecular weight. And this is really just to spread out the data and give you an idea of the different data points that we have. There's 176 data points here. And as we change the R groups, obviously the molecular weight increases as you go from hydrogen all the way to tertiary butyl. And that's why there are these 20 or so sort of vertical lines in the graph. So each point is a molecule with its predicted evaporation temperature. And you can see hydroquinone on the far left. Obviously, it's the lightest of the set. And it has a predicted temperature of around 150 degrees C. Lots of the other molecules are actually more volatile, even though they have heavier, larger R groups attached to them. So let's have a look at the best ones, the ones that have the lowest evaporation temperatures. And I've listed them here on this slide. You can see at 76 degrees C, there's 2-ethyl 5-methyl hydroquinone. Close to that at 79 degrees C, dimethyl hydroquinone. And then a thymohydroquinone at 103 degrees C. And the list goes on, really quite a diverse range of molecules. Some of them are commercially available, as I've indicated there with their CAS numbers, and they have substantially better volatility than the parent molecule hydroquinone. So rather counterintuitively, in this case, adding R groups, heavier R groups, actually improves the volatility. And I think this is probably down to entropy and removing some of the symmetry of the system and making it easier to form a vapor in that way. So that's fine. That's a nice tidy enumeration, but we can do more. We can do larger enumerations. So here I've laid out the strategy for looking at an even wider set of molecules. We could move from 1,4-dithiols to 1,3-dithiols and see if that has any impact. We could change benzene to cyclohexane, and that's shown as possibilities. We could break open the ring and have linear chain molecules, so 1,4-alkenes and 1,4-alkanes, and even 1,3-alkenes and alkanes, and see what effect does that have on the volatility. Maybe these wouldn't be so good for MLD because they might allow the two OH groups to attach to the same surface, but if the R groups were bulky, we might get away with it. So it could be interesting just to see if that's a significant thing for the volatility. So enumerating over all of these, and then also enumerating over thiols, amines, and phosphines instead of the OH groups, and enumerating over all the R groups, gives us a data set of 49,989 different molecules. But the volatility model is very quick to execute. As I said, it takes a fraction of a second. So after about 10 minutes, we had all the predicted temperatures for this set of molecules. And this is the data now. Obviously, it's hard to show 50,000 data points on one graph, so please excuse the lack of resolution. But again, I'm showing the predicted temperature against the molecular weight. And the black dots are the existing precursors that are often used in MLD. The first thing we see, of course, is that most of these data lie somewhere between 50 and 150 degrees C, regardless of molecular weight, really. So there's a weak dependence. The very, very most volatile ones are light and the least volatile ones are heavy. But in between, there's a huge range of molecules that have all manner of different R groups and different masses. And so this isn't really the most important factor, I would say, in deciding whether a molecule is volatile or not. So some of these results might make us rethink how we understand volatility. Here are the 4 molecules that are commonly used. We've talked about hydroquinone. Experimentally, it has an onset of evaporation in TG, so in thermogravimetric analysis, of 132 degrees C. The predicted temperature we've come up with is 150. So other experiments give other values. We look at the next one, 4-aminophenol has an onset temperature of 122 degrees C, and we're predicting around 125, so very close. Certainly the trend is correct. Paraphenylene diamine with 2 amine substituents or functional groups is more volatile, down around 100 degrees C, and 1,4-benzene dithiol with 2 SH groups is more volatile again. So let's look at some of the other trends that we can see in the data. This is comparing thiols in yellow against alcohols in blue. And you can see that the thiols are universally more volatile. We also show here the dithiols and the dihydroxyls. Those are shown with the black circles. In a similar way, phosphines, shown here in orange, are more volatile than the amines, shown in green. And there seems to be more of a spread here across a wider range of evaporation temperatures. Just looking at those amines, so all the molecules that have 2 amine functional groups, here if we go from paraphenylene diamine with the black dot, that's sort of the parent molecule. If we add methyl groups and ethyl groups, the volatility actually gets worse. So you can see 1,4-diamino-dimethylbenzene has a higher evaporation temperature, and the rest of that sequence are the others for us changing those R groups. So this is not the same as hydroquinone. Adding R groups makes this one less volatile. But there are ones that are more volatile, for example, 1,4-diaminocyclohexane. If we change the benzene to a cyclohexane, we get a really good improvement over 50 degrees C in the evaporation temperature. And I've just highlighted there a random large molecule, 3,5-diamino-pentamethyltert-butyl hepdene, which again is very volatile, even though it's got such a large substituent on it. We can look at some of the aminophenols, and again here, adding R groups often makes it more volatile, and changing the benzene to other groups also makes it more volatile. So we see a propanol, a cyclohexanol, a pentenol are all much more volatile. So there's lots of interesting data we can look at here. Here maybe just to check what happens when we go from the benzene core, which is shown here in dark blue, to the cyclohexane core. And actually the evaporation temperatures change very little. There's just a little shift in mass, as you can see on this graph. So how about going to from 1,4 to 1,3 diols and amines and thiols? No difference whatsoever. The 2 sets of data points lie on top of one another. But what does change the data quite a bit is opening up the ring, going from the closed benzene ring to the open butadiene or propene. And this does shift the evaporation temperature down a good bit, probably related to the lower rigidity and the higher entropy of the chain-like molecules. And whether that's useful for MLD is an open question at this point, but at least it tells us what's happening with the volatility. So there I've given you an idea of how 50,000 molecules can be quickly assessed for their volatility, and we can look for new molecules and improved molecules that should help open up the process window, and that we're not constrained by the ones that we've tried before. Sometimes there's some surprises in the data, but it's important to really look at a wide chemical space so as to see those important trends. So we're going to move on now from volatility to the next stage of the process, which is deposition. And here, the tool that we need to use is density functional theory, so quantum mechanical tool, because we're looking at the making and breaking of chemical bonds, and that needs a really accurate treatment. So we're quite limited, as I mentioned before, in the size of system and the number of systems we can look at in a reasonable computational time. But as computer power increases, this is really less and less of a problem. So here are some examples of what we can do. The key thing is that density functional theory is at the base of this, but we build on it workflows that are useful for this and other technology areas. So we have workflows for generating surfaces, for putting molecules on surfaces, for analyzing the energies that come back from density functional theory, and for putting them together into reaction sequences. This is the typical ALD reaction sequence. So atomic layer deposition is a way of growing films in a very controlled fashion, layer by layer. And here we see trimethyl gallium, which is a precursor for gallium, reacting with a hydroxylated gallium oxide surface, as would happen in atomic layer deposition. You can see on the left the molecule chemisorbing to an oxygen, and then proton transfer takes place, and one of the ligands desorbs as CH4, and we're left with a dimethyl gallium fragment, and it starts to bind more to the surface. You see gallium oxygen bonds are forming, and another ligand is lost, and another gallium oxygen bond forms. So this process of reactive adsorption or dissociative adsorption, or adsorption followed by desorption of ligands, this is actually the growth process. This set of chemical reactions, one after another, is how the growth takes place. It's a chemically driven growth process, whether it's chemical vapor deposition, atomic layer deposition, or even etching, as we'll see in a minute. So we have to study each of these reaction steps in order to understand the deposition process. That's the essence of the process. We need to look at structures, as you can see here, and also their energies and the thermodynamics of the process. So that's what the graph shows. It's very easy to take these sequence of reactions and look at their energies on a graph and see the reaction profile. We can see that one particular intermediate is much more energetically favorable than the others. That's the dimethyl gallium fragment in the middle. And that indicates to us maybe what kind of species predominate on the surface for long periods of time during this growth process. So this is a fairly simple reaction sequence, just to illustrate it to you. But you can imagine how we can change the substrate and look at substrate selectivity. We can change the precursors coming in, the effect of ligands, whether ligands decompose and form impurities, and whether different functional groups on the surface interact with one another and what effect that has. So we can really address a lot of the important process questions with these types of quantum mechanical calculations. And going from the simple picture I've just shown you, we can start to build up surface models that really look like what is happening on the surface during the growth process, with different species affecting one another, causing the surface to be covered and saturated. And that's the crucial, certainly for atomic layer deposition, saturation is the crucial thing that drives the process. We can then work out the growth rate and link that back to experiment. Here's another example of a useful tool that can help us understand the adsorption process. This is an example of a gold precursor again, trimethyl phosphine trimethyl gold, adsorbing onto a gold surface. And while the adsorption at 0 Kelvin, so the adsorption in terms of bonding, is favorable, you can see the black dot shows that it's binding with about 96 kilojoules per mole. When you add in the effect of entropy, it no longer becomes favorable for the molecule to attach. This bond isn't strong enough, and the wiggling and jiggling of the molecule is going to lead it to desorb. So it's very important to capture that kind of information. Now, it can be tedious to work out the entropy of molecules and the effect of temperature and pressure. So again, we try to automate this into the software, and you can see the type of output that we get here. These lines show the way the free energy varies with temperature for 3 different pressures that are relevant for the process. And these 3 lines, they're all above 0. So that means that the free energy of adsorption is since the free energy absorption is greater than 0, it means the molecule doesn't have a long lifetime on the surface. It's going to adsorb but then desorb again. And this is actually quite typical of the reagents we see in these kind of growth processes, that they hit the surface, but the reactions are not all the reactions actually lead to growth, and the sticking coefficient is a lot less than 1. Finally, then, if you're looking at thermodynamics is one thing, but you may also want to know about kinetics. And this is the same precursor showing how it actually dissociates on the surface and what's the reaction path for that. It's an activated process, and we've been computing the activation energy. You can see the sketch there of the calculations that went into determining where the transition state is. It's at an energy of 102.9 kilojoules per mole. And of course, the activation energy feeds into then the kinetics and an understanding of the temperature dependence of the process. So having good tools for computing that is also important. And I'm just showing the sketch below how we can efficiently find these kind of steps along the reaction profile, the reaction pathway. So as deposition, we can also look at etch. I mentioned that briefly. And we can use the same tools here because etching is very much driven by temperature. So we need to see those temperature effects. So this is an example of a collaboration with the group of Steve George in the University of Colorado, who's done some really groundbreaking work on chemically driven atomic layer etching over the last decade or so. So we can distinguish between two possibilities. One is continuous etching, which we've just called chemical vapor etching. So like CVD, this would be CVE, the continuous etching of material. In this case, we're looking at titanium dioxide, and it's etching with HF, with hydrogen fluoride. So in one possibility is that it continuously etches away the titanium dioxide as TiF4 and H2O. The other possibility is the HF hits the surface and passivates it and covers it with a layer of involatile titanium fluoride. And that then stops any further etching taking place. And this would be the condition for atomic layer etching, where you have a layer by layer process. You would passivate the surface with HF and then bring in a second reagent to remove that fluoride layer, generate a bare surface again, and go again with the HF. So that would be a layer by layer, very controlled way of etching. Now, which one is going to take place for any particular material, that's not entirely clear. If we look again at the 0 Kelvin energetics, so at the very left-hand side of this graph, you can see the free energy for the ALE, the green curve, is much, much lower. So the energetically favorable situation is passivation of the surface at low temperature. But obviously, with the effect of temperature, the situation changes. And above about 80 degrees Celsius, we predict, the continuous process takes over. What happens is the entropy penalty is just too high for ALE. And instead, entropy favors the desorption of material and the etching away of material as TiF4 and H2O. So the CVE curve, the etching curve, becomes more favorable from 80 degrees C onwards. And this is actually confirmed by experiment. So in Steve George's group, they tried to find that onset of etching, and they were unable to detect any etch products below 70 to 80 degrees C. Above 80 degrees C, they started to see a very faint signal for etching, and then beyond that, the continuous etching took over. So this is confirmed by experiment. So really nice to be able to predict the process window. As I was saying at the start, this is what we're trying to see, is what is the process window for deposition or etching, and modeling can help with that. So the final stage then is the molecule stable? Are we just going to see deposition or etching or whatever the desired process is, or are we going to see these molecules break apart, decompose, and start to incorporate impurities into our film? So the upper limit of the process window is often the decomposition temperature. If you heat the precursor too far, it starts to break apart in a way that is not desired. So we also need to have some information about thermal decomposition. And here again, we're going to look at density functional theory-based tools, but at a more routine, efficient, and straightforward way than looking at exactly what happens on the surface. So to outline the strategy to you, I'm going to use the example of zirconium. So some zirconium organometallic precursors. based on zirconium 4+, and surrounding the zirconium 4+ with 4 ligands chosen from a library. All of the ligands in my library are based on nitrogen attaching to the zirconium center. So these are oxygen-free ligands. Maybe we're trying to make zirconium nitride and it's important that there's no oxygen in the system, or who knows. These were 6 ligands that I chose anyway from, as you know, the very extensive number that would be possible. So this is really quite a small enumeration. The ligands are dimethylamide, diethylamide to see the effect of R groups, cyano, dimethylamidinate. So namidinate has 2 nitrogens attaching to the metal center per ligand, diethylamidinate, and then dimethylguanidinate, which has an extra nitrogen attached to the central carbon. So this is a small library, but it's really just so as we can keep a handle on the numbers that are produced and really look at the data. Obviously, as I showed you at the start, if we had a library of a couple of hundred ligands, we would very quickly get into the hundreds of thousands of precursors. So in this case, we have 6 to the power of 4 combinations, but not all of them are unique. Only 126 of them are unique. And of those, quite a lot are crowded. So we end up with 84 molecules that are not overcrowded. That's the size of the precursor space. But then we want to look at thermal decomposition. So we're going to look at how stable each of the bonds in the molecule are, each of the chemical bonds. And there are 1,280 chemical bonds in this set of 84 molecules. So we have to look at their dissociation. So we need a robust way of working through all the bonds in all the molecules with density functional theory. And that's the kind of challenge for these workflows. You want to really have an automated process. The user should not have to intervene, because that would simply not work for a large number of compounds. So I'll illustrate to you on this example what kind of calculations we're doing. This is my sample complex. It's a diethylamide, dimethylamide. I think there's one, the diethylamide is at the top and the three trimethylamides are at the bottom, and zirconium is at the center. So on this graph, I showed the bond dissociation energy against the complex. So this complex is number 50. So that's why it's just aligned here. And the different bonds in the molecule each have a different bond dissociation energy. So first we're going to look at the metal to amide dissociation, which is depicted here. And if we break that bond apart and compute the energy that it requires to do that and to generate the 2 radicals, this costs 272 or 254 kilojoules per mole. So that's plotted on the graph as the yellow and orange circles. And next we can look at the nitrogen to carbon bond cleavage. Again, there's a couple of possibilities for that, and they're shown as crosses and diamonds. We can look at the carbon-carbon cleavage, which is shown as this particular cross at 329 kilojoules per mole. Then there's the carbon-hydrogen cleavage, much higher in energy, 370, 390, 450 kilojoules per mole. Those are shown as green pluses. And beta hydride elimination is also another decomposition mode where ethene is eliminated, leaving an NH group. And this is a common decomposition route for amides. I think often assumed to be the decomposition route. And in this case, yes, it is the one that has the lowest energy, just 205 kilojoules per mole. So that's how I'm representing the data. That was just the one molecule to illustrate it for you. But as you know, we have 84 different molecules. So here they are listed on the graph, and I've ordered them according to their lowest bond dissociation energy. So that's why they lie in this order. That's the ordering that I've done. That's the numbering I've given them. So the weakest bond is the one that has the lowest bond dissociation energy, and the strongest bond has the highest bond dissociation energy. So we can analyze the data again. I won't go into it in huge detail. So these circles are all referring to the metal ligand bonding. And I suppose we can see the cyano bonds are all very strong, the pale blue dots. The weakest bonds are the amide to zirconium bonds, so the yellow and orange dots, but they're quite evenly mixed. So sometimes dimethylamide, sometimes diethylamide, and in between are the bidentate, imidinates and guanidinates. They're bonding it fairly strongly right across the board. Then we can look at the other bonds, so the bonds in the ligands. So these would be the ones that if these ones break, then it's actually ligand decomposition, and it could lead to impurities. You can see the CH bonds are all very strong, the green crosses. In between then come the carbon-carbon, carbon-nitrogen. Those are the black X's. And often the lowest energy is beta hydride elimination. That's the orange box, but it's not always the most, not always the weakest bond in the molecule. Sometimes those energies are a bit higher. So it's by no means universally the weakest and most favored decomposition pathway. So I'll just put everything back together again. I suppose what surprised me most of all by this is the range of the data. You can see it makes a huge difference how the molecule is put together, what the 4 different ligands are. We don't just get, the 4 different ligands from the family of 6. We don't just get 6 sets of bond dissociation energies. It really matters that a ligand is attached to other partners, and that affects its own bond dissociation energy. So we range from 350 kilojoules per mole on the left-hand side down to as low as 100 or 150 kilojoules per mole on the right-hand side, quite a wide spread. And for the purposes of deposition experiments, or we're just interested in the least stable bond in each molecule. So that's what I'm showing here, the minimum bond dissociation energy for the given molecule. And based on this now, we can start to make a selection. For example, for atomic layer deposition, you really want thermally stable molecules. You don't want them decomposing. They should reach the surface intact and only then lose their ligands, as I showed you in the previous surface calculations. So we would choose some of these molecules on the left-hand side with very high bond dissociation energies. On the other hand, for CVD, CVD works by thermally decomposing the molecules and forming reactive complexes in the gas phase or near the surface, which then start to deposit the molecule. So we would probably choose molecules from the right-hand side for CVD, where we understand how they decompose, and they would do that in the way we want and lead to the chemistry that we want. And here are 2 examples from each of those classes. And I think we wouldn't have predicted that these were some of the best molecules in the set. So that the tetricus dimethylamide is a really good candidate for ALD, and changing it, adding 2 imidinates, turns it into, and a diethylamide turns it into a good possibility for CVD. So a really big difference in bond dissociation energies. So that's the range of properties that we wanted to look at. If you recall, that was thermal decomposition. So that's the maximum temperature, deposition reactions, and then the minimum temperature is given by evaporation. And we have, I think, workflows that are suitable for, say, that democratized view of modeling, where people can just use these workflows to really get to some useful experimental insights. They're robust, they're easy to use, and they allow us to do this kind of systematic searching that is maybe moving us on now to the area of data integration, where we can use the volatility tool for screening tens of thousands of molecules, and then do DFT simulations on hundreds or thousands of molecules to really narrow it down to a set of maybe 10 that can be looked at experimentally. So thank you for your attention. I'll hand you back to Ben.
Fantastic, thank you very much. For those of you that joined late, Simon Elliott is an expert from Schrödinger. Thank you for joining us. If you did miss anything from the beginning, don't worry, we'll send you a link to the entire recording and you can go back and catch up with everything that you missed. We've actually run over by a couple of minutes, so I should probably bring this to a halt now. But Simon, thank you so much. There's a lot of information in there, a lot to get through over the course of an hour, and some excellent questions from our audience as well. So thank you, Simon, for joining us. Thank you to Schrödinger for being our partners for this series of webinars. They're always an excellent partner to have with us. They bring us interesting topics like this that frankly we wouldn't necessarily have had access to otherwise. So it gets us the right people, the right topics, and brings in an excellent audience like yourselves. And thank you so much for engaging with the poll. Thank you for asking your questions. Thank you for sticking around as I overran. So keep an eye on your inboxes. You will get a copy of a link to the recording. Those of you who attended live, you'll get a link to your certificate as well, and possibly a bit more information from Schrödinger on where to find out more. There are links on screen at the moment, for example, but we'll pop them in the email as well to make sure that you can follow them up in your own time. So One final thank you to everybody. Thank you to Chris and Francis from Chemistry World, who've been helping very much in the background here. Dan from Schrödinger has also been helping me to pick through some of the questions and pick out the best ones, combine them where you ask similar topics. So thank you to Dan. And of course, a final thank you to Simon for joining us and for giving us his expertise over the course of the last hour. I'm Ben Valsler, Chemistry World's digital editor. You can find more Chemistry World webinars at chemistryworld.com/webinars. You'll find more upcoming ones with Schrödinger and with our other partners. And while you're there, why not register for a free Chemistry World account? That will mean that you find out more about the webinars that are coming up and also more about our general news, reviews, research, and chemistry culture. So join us at chemistryworld.com. Thanks again for joining us for this webinar. We'll see you for another webinar very soon.